Hi, and welcome to Module 4 of Lecture 3. After the past couple modules full of math that are fairly lengthy, we're going to have a pretty short module now just discussing model assessment. In other words, the question, are models any good? To remind you really quickly, what we had done last time was we had looked at a model of vote choice in which we considered income, partisanship, and ideology, in which partisanship and ideology were thought of as controls in answering a research question involving the effect of income on vote choice. Okay, so how do we assess whether or not the addition of those two additional variables is really good, or if our model as a whole now really captures vote choice properly, or if we're still missing a lot of stuff? So first, consider bivariate regression we had before with just income. We had two different ways of assessing models we talked about back when we were doing bivariate regressions. One was r-squared, which is the proportion of the variance in a dependent variable explained by variance in the independent variable. And one was root mean squared, root mean error squared, which was a measure of sort of the average deviations in prediction. So what do we get there? Well, the r-squared here is 0.04. So we're explaining 4% of the variation in vote choice by income. Where we have mentioned before that we don't necessarily have to care that much about r-squared for a lot of hypothesis testing, but that's still pretty darn low, right? We're not really explaining very much at all of vote choice with income. Now let's add this to the two variables. Now r-squared is telling us how much of the dependent variables variation we're explaining with variation in all three independent variables. And now we've increased a ton from 0.04 to 0.55. We've gone from 4% to 55% of the variation explained. So what it tells us is that we're doing a much better job of explaining vote choice by including partisanship and ideology. We're still explaining only around half the variation, so there's a lot of stuff out there that we haven't taken into account yet. And this stuff might be relevant and correlated with income, in which case our income estimate is still biased, potentially. We still might have a omitted variable bias because we're missing a lot of stuff that still matters, this r-squared tells us. And if some of that stuff is correlated with income, then we're going to have trouble. That said, we're still doing much better than the first regression, which has a very low r-squared. And this is, by the way, one reason to care about r-squared. The lower r-squared is, the more likely there are other things you're missing. There are other things that explain the variation beyond the variables you included. If those variables are relevant and are correlated with the independent variables you included, that could suggest omitted variable bias, among other things. Okay. Also, the root mean squared error declines. So we have less average error in the predictions by including more variables. So this is overall good. These are good things. So let's take another example, a real example from a real paper, about coverage of particular terrorist attack on the U.S.'s coal, and how local casualties, so casualties that happen locally, are correlated with media coverage of that attack. So we're going to take data from 24 newspapers, and then dependent variable will be the number of times the newspaper covered the attack on the U.S.'s coal, and covered that attack between October 31st and December 24th. So independent variables will be casualties, which is a count of the number of people from the newspaper's community who were killed in the attack, and a national dummy, that just is a 1 if the newspaper is a national newspaper, like the New York Times or the Washington Post, or a non-national newspaper, like a local paper. Okay, so we can do this regression in two different ways. One will be looking only at casualties as an independent variable, and the other way, in the first model, includes national paper as a control. In the first model, we have three parameters. So we have n-3 degrees of freedom, which is 21. In the second model, we have two parameters. So we have n-2 degrees of freedom, or 22. So it'll be different critical values we have to overcome to reject the null hypothesis in each case. We see different estimates here. The estimate in model 1 is casualties about 5.6. With a standard error of 0.7, we can eyeball that already. Remember, to get a t-test for these regressions, we divide the estimate by the standard error. This division is going to be over 6. That's probably significant. For the national variable. This is a dummy variable, which means going to the national paper from the local paper increases the coverage by 7 mentions. The error here is 1.8. Again, you divide, and that's also going to be, this one's going to be more than 3, so it's also probably significant. And there's a constant as well for the baseline level of mentions given 0 casualties and a local paper. Model 2 is similar, has a higher constant because you're averaging over the different levels of national local paper, and a lower estimate actually for casualties. Okay, here we see R squared. The R squared here is nearly 0.6, so that's actually quite good. We're explaining 60% almost of the variance in the number of mentions by our 2 variables and our constant. Oh, we explained nothing for the constant. And with the model 2, we explained only 43%. So we're adding 16% explanation in that context of the variance in Y by adding a national dummy for national papers. Okay, so the critical value in model 1 is 2.08. For 2, it's 2.07. As we said, it's a little lower. In both cases, these are all things are significant because the division, the t-test of the estimate divided by the error is going to be greater than 2 in all these cases. Okay, in model 1, about how many stories were written on the call by national newspaper without any casualties? That's a prediction. To do the prediction, we're going to take the constant. We're going to add to that the casualties coefficient, 5.656, times the number of casualties. Here is 0, so we just ignore that. Then we're going to add the coefficient on the national paper times the variable corresponding to the value on that variable. Here we're told it's a national paper, so the value is 1. So it's 9.393 plus 7.107, so about 16.5 or so. If we had 1 casualty, we would multiply 1 times 5.6 and add that to our 16.5, and so on. How about the differences in R squared? Well, we know, I already said this, the R squared is greater for model 1 than model 2, so we're explaining more of the variance in our dependent variable in model 1 than in model 2. Similarly, the root mean squared error is lower in model 1 than model 2, so we have less overall error in our predictions in model 1 than in model 2. Whether or not you think it's worth it to go from model 1 to model 2 given this variable, it's up to you. I think in this case it's a fairly decent size improvement. But we know the casualties estimate does change, but not as much as some of the other estimates that we've seen so far, like income. Okay. And that's it. All this really was is discuss R squared and root mean squared error in the context of a multiple regression and to provide another example of a multiple regression to look at. In the next and last module in this relatively short lecture, we're going to go over some one problem and get a sense of how this all works. Another example of how this all works. Thank you very much.